mean, and so we are very fortunate today that Dr. Ray is with us.
Yes.
And yeah. So Ray has
I don't see it on here.
Tell about Ray.
That puts it over there.
In
I'd like to see it full screen.
So I consider Ray as a physicist plus agriculture agrometeorologist, both because we have seen that his kind of contribution to Canada and especially to the whole world, particularly on the GHG emission, then climate, is it's fantastic. And he has written 2 books. He will also mention the 2 books which is related to the air quality and health, this air and the agriculture. And he has clearly mentioned in the contribution of WMO that how this kind of emission and climate can be taken in very positive way of agriculture or like that. So I will just stop here. So we'll hear Dr. Ray. So Dr. Ray, welcome to today's webinar, and really on behalf of INSAM, and we just appreciate your kind of kindness that you have immediately agreed to give a lecture. So over to Dr. Ray. I will request all of you just to
hello to you, right?
Pardon?
He said hello to you.
Yeah.
You say hello to me?
No, because you weren't on here.
Yeah.
There's some people still talking, but thank you very much, Dr. Nabasu. I will try to share my screen, and then we'll go from there. I'm really pleased to come and talk to you about
this is us, but I don't understand how you can turn the camera around.
Yeah, our agrometeorology has evolved over the years. So I'm going to talk about 70 years of share my screen. I guess we should have practiced that. Okay, here it is now. So it's going to work now. So I'm going to let me know if you. Yeah. Okay.
Who's that? Raymond.
Yeah. Once again.
We're going to turn the camera.
Yeah, I know.
Can you turn the camera off?
Yeah, Ian, you should turn your voice off. Okay. So today I'm going to talk about the evolution of agrometeorological research from a Canadian perspective. Nabasu, do you see that?
There we go.
You see the screen, Nabasu? Yeah. Okay. So
yes, we can see. Yeah.
Okay. Thank you very much. So I'll cover quite a few. About 7 topics. Agrometeorological research from the 1950s to 1970s. And then there was a fairly good shift where agrometeorology became a bit more like micrometeorology, and we measured and modeled mass and energy exchange for a wide range of ecosystems. And then we started quantifying agricultural greenhouse gas emission and the carbon footprint using life cycle analysis, impact of agriculture on climate. And then we started looking for natural climate solution, and I'll show a team of scientists in agriculture in Canada have tried. And then the latest thing is Living Lab, which I will say a few words about.
Are you looking for the Bluetooth? I can't get the Bluetooth on the television either. I don't know where it is.
Ian, we hear your voice, you know. Okay, so agrometeorology in Canada started basically in 1951. Canadian Met Service saw that agriculture did not have any meteorologists, but Forest Canada did not have any meteorologists. So they seconded one of their meteorologists to agriculture, and George Robinson was the one seconded, and he arrived here in 51. And before that, there were no meteorologists in either agriculture or forests in Canada. So that was quite a major breakthrough. And George was paid by the Canadian Met Service throughout his career. And when he arrived, he set up a program where he planted 8 different crops at different locations in Canada, and for many years they observed the change in development of the crop and all the stages of growth of the crop, and measured the yield at the end of the season. And this was a real nice data set that I used later on in my career. But one of the paper that he wrote based on this data set is a biomet timescale for cereal crop involving day and night temperature and photoperiod. He wrote that in 1968. And one of my colleagues in United States Department of Agriculture, Thomas Sinclair, 50 years after he wrote in Crop Science, George Robertson provided key concepts used yet today to describe the pace of plant development. That was quite a compliment, because not many of our researches after 50 years is as valuable as what George did. And if you might, if you want to see the history, George in 1989 wrote a book, and it's available on the internet, The History of Agrometeorology, and it talks of the beginning, the role of Canadian Met Service, and all this, and it's a very nice, informative document. And to put things in perspective, I should say that the Commission of Agricultural Meteorology was established in 1953. So, and a lot of the things that I will say, we work very closely with the Commission of Agricultural Meteorology, and throughout these 70 years that I'm reporting. And after, when George retired, Wolfgang Bayer was hired became the section head of agricultural meteorology, and he's well known for having developed the versatile soil moisture budget, which is still used by many scientists. And he developed a model to better understand the factor influencing crop yield. He was also the 4th president of the Commission of Agricultural Meteorology from 71 to 79, and really, really active throughout his career with the Commission. And to put things in perspective, like in 1971, the Canadian Met Service became the Atmospheric Environment Service under the Department of Environment. It's still that. But before that, Rudy Tritle was the agrometeorologist in Canadian Met Service, and he wrote a handbook in 1978, which contains all the meteorological data from 1941 to 70 for 200 climate stations representative of the climate in agriculture, and 35 climate stations representative of the climate close to the forests. So, but because of climate change, I must say that results from agromet studies need to be re-evaluated because
sorry to disturb. Sorry to disturb. I'm just requesting Dr. Sable, please mute your system. Mr. Dr. Sable.
Thank you.
We can't hear Dr. Ray. Please mute your system. Dr. Sable. Okay. Okay.
Thank you very much. Thank you very much, Dr. Nabak. Yeah.
Okay.
It's important to realize that, because lots of the studies that have been done, like I wrote a paper in 1980 using the data that I just mentioned, that George Robertson had collected, a team had collected, and I wrote a paper on determination of the importance of various phases of wheat growth on final year. Like we have planting to emergent, emergent to jointing, jointing to heading to flowering, flowering to soft dough to ripe. And so, but I am sure that the critical phases would be different now than they were in 1980. So it's important to realize that we need to continue doing agrometeorology, and even more because of climate change. So another paper that was written by some of my colleagues and I in 2013, which was Ward Smith, assessing the effect of climate change on crop production and greenhouse gas emission in Canada. And for winter wheat, using historical data from 61 to 90 and future IPCC scenario, climate scenario 240 to 269, Smith et al. Predicted substantial yield increase in winter wheat. However, just recently, I just saw a paper by Coulon de Perez and colleagues in the Journal of Climate and Earth Science, and they use a technique called the unseen approach, which is unprecedented simulated extreme ensemble, and they predict substantial reduction in winter yield in the Midwest, like for once every 6 years, due to frequent air temperature over 32.8 degrees C, which can cause enzyme breakdown. At least they predict that it will be there'll be some substantial yield reduction, and this was not contemplated in the paper by Smith et al. In 2013. Another one that I was involved with, one of my colleagues, Sam Carabata, he developed an indicator to estimate the tree scale damage to fruit trees in the spring, because with climate change, the springs are warmer. They're 1 year out of 10, right? Presently, there's a lot of winter kill the flowering trees because the trees flower earlier, and then there's considerable damage. And that repeat period will undoubtedly become shorter and shorter. So now I've covered the 1950 to 70. Big change in research happened in technique of measuring photosynthesis and transpiration and mass and energy exchange for various ecosystems. As part of my PhD, which I did at Cornell, I developed a new technique of measuring CO2 flux at the field level. Until then, there were a few measurements with using gradient technique, but most of the measurement of crop growth were done by measuring the yield at the end of the year, or once in a while, collect plant material and measure the change in dry weight. And you can see, for example, that if a crop absorbs 1.6 grams of CO2, it's equivalent to 1 gram of dry matter. So we're able to measure the rate of growth of crop instantaneously with this technique. And later on, one of my colleagues, Francois Charineau, and our team, we developed a CO2 water vapor analyzer that we could measure now evapotranspiration. And this technique is used. These techniques are used worldwide in all the Ameriflux, Asia Flux, and all these different group. And it revolutionized a lot of the work. Here are a couple of publications which were discussed scaling up plant process from leaf to crop canopy. Two of my colleagues wrote papers on how to estimate from leaf chamber measurement, can we come up with crop canopy measurement? Now with the flux technique, we had canopy measurements. So Elizabeth Patty wrote one with using leaf chambers, and it showed how it is quite difficult, but you measure the photosynthesis at leaf level, at tree level. She was able to determine the importance of different level on the total flux. And Philippe Rochette did something similar where he used a Penman-Montiel equation to calculate the canopy conductance and see how, by making individual stomatal measurements on different levels of the crop, using shaded and on sunlit leaf, he was able to come up with estimate of the canopy from individual leaf measurement. Both groups demonstrated that it is quite a complex way to do scaling up, though. So,
I'm turning it off.
Yeah.
Yeah. After that, it was a lot of progress in Canada. Gordon McBain, for example, measured evapotranspiration using an aircraft, the aircraft of National Research Council. And so one engineer working with me, Adrian Brack, developed an open path CO2 analyzer that we were able to install on top of that aircraft that belongs to the National Research Council. And we could fly. At first, we used to fly at 5-10 meters above the crop, but eventually, normally we fly at 50 to 100 meters above the vegetation, and can measure the rate of growth of the crop. Here, for example, we measure vertical wind and we measure the CO2 concentration. So when there's an updraft, air going up, the CO2 is reduced because it's been used by the crop. And when it's a downdraft, it's fairly constant. CO2 is fairly constant. Well, it decreased by about 20 parts per million. And you see there in these pictures that this was done in 1980, and the concentration of CO2 was only about 320. And now, in the last month or so, it passed 420 parts per million. So, and that's carbon dioxide is the main greenhouse gas causing climate change. So it shows how serious the problem is. And to get the real flux from the aircraft, the flux of CO2, you have to pass a few times here, and you take the average because transport of gases is not a continuous process, you know. Another time the updraft might be here right in there. So, but if you pass 2 or 3 times, you get the mean flux of carbon dioxide, and you can get the same thing for evapotranspiration and other gas. So, with this technique, we were invited by many flight research. Ian McPherson, Peter Schripp from McDonald College, and I were invited to go and participate to many international field camps in North America. We met with Japanese group and Jun Kim from Korea, and at the time he worked with Shashi Verma from the USDA, and we measured in Manitoba. I'll show a bit of that. We measured there was a big campaign, FIFE, over grassland, which is FIFE is the first international land surface climatology field experiment over grassland, and Southern Great Plain experiment, boreal forest code. I'll talk mainly a code of California ozone deposition experiment. I'll talk about these 3 mainly here. Oh, and this one too, the northern wetland. So this is the FIFE experiment where we were Pierre Sellers organized this, and I had taken a sabbatic leave in France, and I met him there, and he said, "Ray, you must come with your airplane and measure. We're starting this program. We have scientists working at the leaf level. We have some at the tower level. We would like you to measure fluxes at the we have people doing spectrometer reading, and we have satellite data here. So it was a wonderful experience to work with all these colleagues. And so here I show we would fly at 90 meters above the crop. We'd fly like this, and this is 15 kilometer wide and 15 kilometer, and instantaneously we would get the flux of CO2, for example, in kilogram of CO2 per hectare. More people might be more familiar with milligram per meter square per second, and it shows almost perfect correspondence. This is not much green vegetation here, and this is very green vegetation. This is a Russian satellite, but now there's all kinds of satellites that measure it. This measures NDVI, which is NDVI is incident radiation, infrared radiation minus red radiation over infrared radiation plus red radiation. Infrared is around 740 from this, and red is around 640. And here you can see there's a little bit of problem sometimes, though, because there was a ravine here, and it says there was large CO2 flux, but I think it probably was not knowing how to work with the effect of a ravine. But basically, we were getting fantastic results. And we measured evapotranspiration. This is in millimeter per day, because in those days we talked about that. But to get to watt per meter square, you have to divide by 0.015, and you get watt. And this is the Conza Prairie, and the sensor of the vertical wind was here, a pressure sensor, and We had an ozone sensor here, and all the other sensors are in the back of the plane, and we adjust for the delay in sampling, measure vertical wind and the concentration of various gases. So after that, that was in 85, 86, 87. We were invited to the northern wetland and study near James Bay. We had northern wetland represent this, these are peatland. They represent about 13% of the land surface in Canada, and we don't know. We did not know much. We at the time the idea was also to measure methane. Our methane analyzer in those days did not work, so we measured other fluxes, but now we're able to measure methane from the aircraft too. So it's really regrettable that at the time it didn't work. But peatland, Canada has about 50% of the peatland in the world. So, and Russia is about 20%. So it's important to understand how the system works. So what we did here, we flew 3 transect on the. We did many things, but at 30-meter, we 380-kilometer transect and over these wetland. We call region 1, region 2, region 3. So on many different days,
Hello?
these are Julian date, So and so we would fly these 3 transect, and we measure the CO2 flux and the temperature of the air, and you see quite interesting that as the temperature goes up,
यहाँ पे
the
जो है
flux
ना
goes
सर
down.
अ,
If CO2 flux is less,
आदमी जैसे
usually
एक
in
एम्ब्लम है
the
उसके ऊपर 22
agriculture
दिख रहा है, देखिए
system, the temperature is not the dominant
वहाँ
factor
पे क्लिक कीजिए।
unless it gets to be very
हाँ
high. It is more
हाँ
radiation.
फाइंड कर लीजिए वहाँ पे वो
There's a lot more in this data that now that we understand things better and we want to look at ecosystem, we could do a lot more. And one of my colleagues, Yang Lee and Jun Kim, are thinking of using some of our data, and I'm thinking of working with them to try to study these different ecosystems. And now the sustainability of these systems is changing with climate change. So it is quite remarkable, and there's so many things we could do with this. That any young person interested in using this data is available. All our data is available, and we would be delighted to work with this. We have somebody, Devin Worth, is custodian of all this data, and it would be very nice to work with him. So another experiment that we done is California ozone deposition. They want us to measure how much ozone damages crop, but the amount absorbed by the crop the damage is a function of the amount absorbed by the crop. So we flew all different over. This is in California. Most of the land is irrigated, but we flew over a lot of cotton and crop. We flew over this area and measured what we call the NDVI, which is again IR, infrared radiation minus red over infrared plus red, and we compared with the flux of ozone, and we did that over grape orchard, grass, cotton, and the regional run, corn, and we found there's a very good relationship between we call the velocity deposition of ozone. But if you want to calculate the flux with this relationship now, you can calculate the flux of ozone. If you know the concentration of ozone in an area, and if you know the NDVI of the crop, you can calculate how much ozone is absorbed by the crop in California. And this is a lot can be done on that. And we were paid by the California Ozone Board to come and do this, and it was quite a nice experiment. So another experiment that we did, again organized by peer sellers, with many Canadian scientists and many scientists from all over the world came and studied the boreal forest with us. It's called Boreas. We did that 1994, three period in 1996, one period, 3-month period in 1994, and again we we see here pure cellars. We see that we're flying over the forest, and there were many tower systems over different ecosystem. And this is the Boris symbol. So one of the things that pure cellars wanted to know is how can we scale up. So we took certain section in northern Saskatchewan and southern in Saskatchewan, and we flew this, and we had tower-based system over black spruce, jack pine, aspen, and fen. And so we decided to fly a grid many times and see how well we could relate, knowing the area of this ecosystem, and the tower-based flux were around. They were not necessarily here, but they were all around. We tried to scale up and see each with the aircraft. We measured the flux and how well we did relate scaling up tower and aircraft-based flux measurement to obtain regional flux. And to get the flux like this, you need to know a lot about the footprint. And Peter Schrepp developed an excellent model where you could model the footprint of any flux measurement. It varies with time. Any macromet measurement varies with turbulence and all this, and the stability condition and all this. So, but with this information, we like all on these days, we estimated the flux and we measured the flux. And here I show CO2, but we did all the other one too. And if we had more time, I would have shown how we do with all the. But we're doing fairly well, But there's still a bit of discrepancy between the estimated and measured, which if I were younger, I would pursue that a lot because there's a lot that can be done to figure out how to improve these estimates. So changes in some of the major could have a substantial impact on climate. That's why, as I was getting older, I got very interested in looking at more than all the land area in Canada is 1 billion hectares, and agriculture covers only 7% of that land, and 4% is intensively cultivated, and the rest. That's 40 million hectares, and 28 million hectares, which is the 3%, is natural grassland. So it's knowing that there are not too many scientists who look at the whole ecosystem, all Canada. So it's important that agrometeorologists who have experience looking at an ecosystem very closely, and forest meteorologists too. We start looking at other ecosystems. So it is very important to understand the impact of other ecosystems, such as forests. Forests represent about 50% of the land area in Canada. Wetlands represent 13%. Tundra, pretty much the rest. After agriculture, 7%. I'll talk a lot more about this. But for example, Canada is proposing to plant 2 billion trees to combat climate change. However, it's important to realize that some trees, like conifer, make the land surface darker, leading to more absorption of heat from the sun. Alan Betts from Vermont wrote a nice paper on this topic, which I will show in a few minutes there, and it shows that reinforcing due to forests is quite huge. Net radiation over a forest is huge compared to over grassland, and it causes warming. So we'll see a lot more about that. Some trees produce volatile organic compound, such as isoprene. Like one of my postdoc, Tong Zhu, who now works in China. He's a dean of one university in China. Wrote a paper with us on this, and Jim Salinger is very interested in that, which isoprene organic compound. They mop up the methane destroying hydroxyl aldehyde OH in the air, and these are the compound that molecule that destroy the methane in the air. So if other compound destroy these the hydroxyl, then there'll be methane lifetime will be longer. So right now it's about 11 years lifetime of methane but on a big scale it could have a lot of influence. So it's important to be aware of that. Then in certain region, it has been shown. One of my colleagues, Pierre Bernier, wrote a paper that after a forest burned, sometime in eastern Canada at least, lichen is formed, and lichen reflects the radiation more than which is good, reflecting radiation, than forest. So sometimes it's not beneficial to replant the forest after it's been burned. So these are all things that we must consider when we think of all the ecosystem. Here's the slide that I mentioned before, for example, by Alan Betts, where he shows the net radiation over conifer forests, over grass, and over deciduous forests. And he shows on an annual basis, this was done as part of Boreas. He shows on there's 14 watt per meter square difference between conifer and grassland. 14 watt caused a difference of 7 degrees C. 1 watt is half a degree C. So for example, if we had conifers all over the world, the earth temperature would be 7 degrees warmer. So Alan was working with the weather service in England on that, and before they realized that, the temperature prediction for the boreal forest was 7 degrees wrong. Because that they were assuming that nobody had measured the albedo over boreal forest, so they assuming it was like grassland. And the deciduous forest is 3 watt per meter square. And one thing that is very important to remember, currently the sensitivity of the global climate is 3.7 watt per meter square for a doubling of atmospheric carbon dioxide. So if the CO2 concentration in the air increased from 288 to 560, 460, it would be substantial, but you see this 3.7 is of the magnitude that we're talking here. So it's important to understand these systems. One of our colleagues, Zhang Liu, is doing a lot of work looking at albedo for different uncover. I think that's the tool that we have at the disposition to look at different ecosystems. Like Zhang just gave me that recently, where he put the land cover for different vegetation type, and he shows he has this for using MODIS data at 250 meter resolution. You have that every 10 days from 2000 to 2022. So he shows here, for example, the summer albedo and the winter albedo, and you can see that, remembering that a change in albedo of 0.5% resulted in a radiative forcing 1.7 watt per square meter. You can see that there's a lot of things happening here that we should be aware. And he gave me this nice slide yesterday where he just did something for the Peace River lowland. He calculated, he estimated the albedo for cropland, for grassland, for needle leaf, and for broadleaf. And this is based on 100,000 pixel for each land cover type. So he's averaged it every 10 days for 23 years, So this has not been published yet. They just gave me that yesterday, actually. So it shows a huge difference, and there are a lot of calculations. I'm sure he's going to write a paper on that soon. So now we've looked at all the ecosystem. So quantifying agricultural greenhouse gas emission has been something that we've tried, and we've made a lot of progress. People use chambers. laser, open path laser over manure storage tank, tower flux system, an aircraft, and even sometime balloon, or you measure at night. There's the nocturnal boundary layer is about 100-meter deep. So if you measure the concentration, change in concentration in the first 100-meter, you can get a pretty good estimate. The footprint is about 1 kilometer, and you can get a pretty good estimate of the Elizabeth Paté. I'll give the paper after, has written some nice paper on estimating nitrous oxide with this, but she puts a little tube on the balloon and measures the concentration on the ground, the mean concentration as you go up and down, and for methane, CO2, and N2O. These are the one, but they all combine with, they all have a different scale and time and different area that they see. I think the previous slide might have talked more area, like 1 meter square, 10 kilometers square, and days. And the thing too is you need models, and you need satellite to really scale up to and model. So the combination of all this is what we've used to learn a lot about this greenhouse gas emission. Here are the two paper by Elizabeth on the scaling up, on estimating nighttime CO2, methane, and nitrous oxide emission, and these two reviews have been written very recently. Here I reviewed all the work we've done with the aircraft. Tom Spoken wrote a book, and it's quite nice. We measured, for example, things we reanalyze after. Now that we had measured things we never looked at. For example, in here I report all the flux over different cities, and I report the flux at night. At night, where we show that 100-meter high, there's no flux. The flux is zero because the boundary layer, the inversion layer, stops any gas escaping. So you have now a bigger chamber to measure the flux of gases. But we have a bigger chamber, but this chamber is the one that has been used for, chambers like this have been used, most commonly used to measure greenhouse gas from agricultural soil. Like Philippe Rochette has done a lot of work on that with us here. But with Dan Pennock in 2005, people were measuring chambers, and we were measuring with the airplane the N2O flux, and it showed that they were measuring in spring bursts when the snow was melting, and of N2O, and there's no doubt that chambers were affecting the measurement. So what we're measuring with the airplane was later than what they were measuring with the chamber, because where they put the chamber, they were melting the snow around, or the little things like this. But it's quite, there's lots of publication on that. So one technique that has been used a lot by people like Tom Denby, Laurie Harper, and Tom Flesch is to measure methane source, micromet mass difference technique, where you measure upwind and downwind, and you have gas releasing gas, and you have these open path lasers that measure the methane and CO2 concentration and ammonia concentration. And this shows sort of the accuracy. We had a source here, and we changed the concentration of the source, and we were getting a confidence about 5%. Just putting in perspective, 40 milligram is equivalent to 10 dairy cows. So this is about 50 dairy cows. The length of the laser should be at least 6 times the width of the source area, so that when there's a small shift in wind direction, you can detect that. But it works. It's quite accurate. Another technique that is probably even used more is just called the inversion dispersion modeling, the backward Lagrangian stochastic technique. And there's you can download, WindTrack can be downloaded to do the calculation. And basically, you just need to measure, have an idea what the concentration is upwind and downwind of the source. You can use laser, or you could use a tube, perforated tube, and measure the mean concentration downwind and get the same thing. And the CL is CB is background, C downwind, and you need to have a sonic anemometer that measures certain characteristic to be able to use the wind track packages. And you have more confidence in the momentum cuff length is 10 meter, greater than 10 meter, and the friction velocity is greater than 0.15 meter per second. But there's Tom Flesch and many others have written many papers on that. And Andy van der Zag is now using that full time, and I have a colleague in China, Jilin Gao and other using it in China. And here I measured with some colleague over a feedlot in Alberta, and we measured that for several days. And you can see we measured the methane emission. It was about 1,200 cows in the feedlot, and we measured downwind of the feedlot, and it shows the one measurement would not be very good because after the animal they eat in the morning here, big increase in methane emission, and later on they have a snack in the evening, another increase. But we learn things like, for example, the YM, which is methane conversion factor, is for gross energy intake, is about 3 over in the feedlot, and in the poor pastures about 15. So the efficiency of digesting the food, the better the food is, more refined the food is, the more the efficiency, less methane emitted. This is the emission factor if the quality of the food is better. So we wanted to verify the agricultural methane emission inventory. So we very lucky we have the milk quota system in Canada. So we're able to know exactly how many dairy cows. This is mainly dairy cow section in Eastern Ontario, and we know exactly where the cows are. They're all in the barns because it's such a big production. They don't even go out most of the time. The animal there, and so we flew different transect. So and here there were a lot of. I knew the wind was coming from here, so I will just show this. But we measured many different places, and it was a joint project between Environment Canada, National Research Council, which we worked with enormously. These guys like Peter Schripp and Ian McPherson have been fantastic cooperators there, and Agriculture Canada. So we show again. We picked this transit here, and shows how we calculate the methane because we know where the animals are, how many, and we also use information from Andy van der Zag had also measured the amount of methane per certain barns, and we verified, made sure that all the animals were accounted for, and we use a footprint model. So when you fly here, for example, this is a 10-kilometer transect. Sorry.
Sir, कुछ questions पूछूं क्या
The contribution to the flux is a lot more here than here, and only 10% here.
Interdependency of gases.
So it's important to we use a footprint model.
Sir, उनका admission का process चल रहा है तो
and here's the result that we compare with the inventory. And several flights here, we just took the standard deviation, and here's what the aircraft measures. But it measures pretty much the same here, but measures a bit more here. But you look at the land use, and there are wetland. There was some wetland in one section a little bit, like and none here, not very little here. So, and this is the amount of agricultural land. So it was no surprise that we were measuring slightly higher here because there were wetland emission here. So wetland methane. So, but when you do inventory work, you have to be quite concerned that there are other point sources and they can be substantial. Like, for example, I will show here one that's in between Ottawa and Montreal, and we measured the flux in 210, and it's called La Flèche, and it's a waste treatment facility, composting, and it shows where it is. And here you see the view, and we flew many flights around, and we wrote paper. A colleague from China wrote a paper, but we have a lot of data here, and we showed that the methane emission from this waste treatment was 2,000 kilogram methane per hour, which is equivalent to 130,000 dairy cows. So and these are very often they're not accounted for because people don't know. Like now, if we went there, probably they're doing something different. They're a biodigester or something, and maybe they're not emitting this. They may be using the methane for something else. But I've worked with producers, and a long time ago they had biodigesters, but sometimes they did not have the system to flare, or the system was in the barn and not working. So one has to be quite concerned that aware of what's going on there. But Tom Flesch also look at fugitive emission from a biodigester, and here it shows like a biodigester is a very good way to convert manure to methane, but they have different level of efficiency, and the flaring techniques sometimes are very efficient, sometimes they don't work well. Here, for example, he's measured 80 kilogram of methane per hour, which is huge, remembering that's about 5,000 dairy cows here, but just for an instant. And maybe they were just venting it, maybe they were not flaring it, I don't know. Because most of the time during the flaring, the methane were a bit bigger. They were about, flaring eliminated 2%, 2 kilogram per hour. Average fugitive emission were 4 kilogram, which 2% of the gas production. So it's still very efficient to use biodigester because you get 99% of the gas production. So other things, measuring N2O at the regional scale. This is N2O as nitrous oxide is one of the greenhouse gas that is important, and it's very variable in space. So we took the airplane and measured two transects about 10 kilometer long, and we're curious. We developed a technique. I had developed as part of my thesis the accumulation technique, which is a technique that if you don't have a fast response analyzer, you take the gas, absorb and collect the gas proportionally to the vertical velocity. And later on, Jim Biosinger and wrote a paper, the relaxed accumulation, which you don't have to do. It's simpler. You just have to measure the conversion up and down, and it makes it a bit simpler. And this is what we use on the plane. And these two areas during snow melt, we show that they were not identical crops, but fairly similar N2 emission during snow melt associated with these two agricultural regions. And these emissions associated with snow melt are about spring thaw. They're about 30% of the total emission in Canada. Here, Ward Smith developed a model with DNDC to predict N2O emission, and for these regions. And we were flying the airplane, and we were measuring on certain days. And the agreement is fairly good, model is not perfect either, but in general, the aircraft was measuring a bit bigger flux. For example, this year we just in 2000 we just studied spring thaw, but other years in 2001. But the other 2 years we studied spring thaw and planting, after planting. And you see the peak after planting. Here, the plane did not get it here, well, because maybe it happened later or before, I'm not sure. But the agreement is pretty good, not perfect, but uh, so here are some tower-based measurement of NTO over spring wheat. Elizabeth has had this system running for many years over different crop here. Show tower-based, and it shows the snow melt or spring thaw, and the emission after planting, because you put fertilizers here, and then depending on whether you get rain. So this type of data has been used enormously by Ward Smith and other people who use model. And here I show the comparison of the model for many years, from 70 to 2000 of the 99 of the total N2O emission using the model and estimated spring emission. And so this type of information is very useful to improve our inventory. So carbon footprint using life cycle analysis. We use an holistic approach. Here we're trying to estimate greenhouse gas emission from milk production, and we have to model everything. The population of dairy cows, the methane emission from enteric fermentation from their manure, based on the feed ration, the methane emission to grow the crop, and the N2O emission associated with growing the crop, and CO2 emission associated with fertilizer production, and all these type of things. We count everything pretty much, and we develop all kinds of model. Like we have different level of complexity and intended users, and a group like Ward Smith and Brian Grant did a lot of work with Descent, and there are a lot of teams in the U.S. too. Chang Lee, who died now, but process-based model for crops. Ulysses and carbon CAFU square. I will show that after. And F4E2 is fossil on-farm and off-farm fossil fuel use. And Jim Dyer has been the person who's done so much work on that. Like normally, fossil fuel emissions from fossil fuel use in Canada are counted with transportation and all this, and not with agriculture. But here, since we want to calculate the carbon footprint of agricultural food, we've a lot of work on that to do that. And then I'll say a few words later at the end here on OLOS, which is these are simpler and they get more complex. And OLOS is what the calculator to calculate the greenhouse gas emission on farm emission by producers, and I'll show you something on that. So now Descent is quite a sophisticated model, and it's used for carbon footprint of all. So F4E2, for example, the one that general farm energy budget, you have to count direct energy on farm decision, direct energy types. And, Jim Dyer did a lot of work on that, and Michael Babcock from McDonald College is trying to find this on a finer scale and having more crops, and he's doing a PhD on that, and it would be very useful information when it's completed. So the other calculator, that I mentioned, Ulysses, is a unified livestock industry and crop emission estimate. The person who's done the most on that is Xavier Verger. He now works in France, but he spent 17 years with us in agriculture, and he's developed this model. And Dominique Maxime has the CAFU square, which is Canadian footprint calculator, and it calculates the emission up to the exit date of the producing plant or the farm. So here I show we have to use CO2 equivalent if we want to compare the other gases. Here we calculated the amount of greenhouse gas from fertilizer supply, from field work, from machinery supply, from electricity, heating, fuel, on-farm transport, and this account to, in 2006, account for 26% of the greenhouse gas emission in agriculture in Canada. And agriculture emission are about 12% total if you count these. Otherwise, many people still don't count these because they are counted by the industry. And nitrous oxide emission and methane emission to 46% and 26%. Okay, so manufacturing of fertilizer is the largest single source of CO2 emission from fossil fuel. Jim Dyer wrote that paper, several papers on that. And here I show the emission intensity of crops in Canada. Jim Dyer calculated that for 2010. And it shows the ton of CO2 equivalent per hectare or ton of CO2 per a ton of dry matter. And you see some these crops like this. Heavily fertilized crop have a huge emission per hectare, but when you look at them per ton of dry matter, so they're not as big because they're very productive, you know. So we calculated the emission intensity of crops all across Canada by province, and that's what Michael will do: more crops and more regions. But it shows quite a range of. So if we want to be specific, we need the information at the finer scale, you know. But we're not ready for that yet. But most of it is at the national scale right now. But it shows huge differences. For example, usually because the N2O is larger in eastern Canada, very often, like for example, it's much like the methane emission from growing canola, for example, is much greater in eastern Canada than in western Canada. You know, all kinds of things like this that are. It takes a long time, but there are all kinds of reference that I've got the help. So to calculate the carbon footprint of beef, we have to know what they eat, the feed ration. Here I should, or if you want to calculate the feed carbon footprint of milk, for example, we know what dairy cow eat, and based on what they eat and all this, we come up with the amount of greenhouse gases produced for different milk product, for example, for cheese, for the per kilogram of product here. I show cheese, cottage, cream, all kinds of milk and milk powder, because it takes Xavier Vergier did this publication, and it's because if you, for example, you need a lot of milk to produce a milk powder, a kilogram of milk powder. So based on this, you know, like and butter, for example, per kilogram of product, it's bigger. So calculating the carbon footprint of beef, then, for example, in order to calculate the carbon footprint of beef, we need to count all the greenhouse per kilogram of live weight for bird until it leaves the farm. And, you know, you calculate all the CO2 emissions associated with fossil fuel use, farm field work, crop production, buildings, electricity building and all this, equipment, machinery and all this, the manure. Been a lot of time doing this kind of work, and comparing emission between animal type is quite complex because there's one primary function is per unit of protein is one way to compare emission between animals. So here we show the methane emission in kilogram of CO2 per kilogram of protein. For beef, for example, is 5 times more than pork and 10 times more than chicken. but they show lamb, for example, and milk production per kilogram of protein. So this is quite important. So and greenhouse associated with protein of plants too. Like ton. So, for example, you have 200 times more greenhouse gas produced a ton of protein in the West versus a ton of protein from soybean versus beef. Do you see a difference between Eastern and Western Canada? Because uh, part of the allocation of the protein, the emission is allocated to milk production. So out in Eastern Canada, most of the herd that produce beef is a dairy herd. So there's all kinds of things like this you have to take into account when you calculate the carbon footprint per ton of protein. Like pulse crop and soybean represent a far less carbon intensive method of producing protein as compared to ruminant and non-ruminant pork and non-ruminant. For example, the amount of feed input for ruminant equals 15 to 30 times the mass of the final meat product. So it's not surprising that the carbon footprint of beef would be much larger. So I'm getting close to the end here. So I know I passed my almost. The potential role of consumer to reduce greenhouse gas. It is a nice little study that Jim Dyer and I did recently, which in Canada, Canadians consume 391 kilograms of protein per year. And we are all encouraged to reduce red meat consumption. Red meat consumption is pork and beef. And if we reduce, now we have 50% pork, 50% beef. And if we reduce that by 24%, we would reduce the emission by 4 million tons. By the way, 4 million tons here, if we reduce meat consumption from the agriculture sector. And the agriculture sector produces almost 70 million tons. So it's not, and if we did a split, say, rather than eating 50% pork, 50% beef, we would eat 75% pork, 25% beef. We would reduce the emission further 9 million tons. Already, just a little thing like this, consumers could reduce emission 13 million tons, which is out of the 70 is quite considerable, like without too much sacrifice. And so we wanted really to get the message across. And it's not easy to convince a consumer to read our paper or to try to understand that. So Jim Dyer was really strong on trying to make a video, get a video made, the science video to using protein as a unifying measurement of livestock carbon footprint. I won't show it right now because I'll show it at the end of the talk in a few minutes, rather than because it could. But really, it's a 3-minute video, which when we tried it with Dr. Nabatsu yesterday, the music didn't come out, just the word were coming out. So I'm not sure if it will come out today or not. So the idea is to what we end up recommending is you keep on eating beef, but maybe from the 28 million hectares that we have, regenerative grazing, and eat more pork, and consumers will have done a very, very good thing as far as their contribution to reducing the emission per year. So we'll look at that. A few publications that covers this here are all documented. So impact of agriculture on climate is quite short. We had an expert team with the Commission on Agriculture. I didn't mention the Commission enough, but throughout every 4 years we met with the Commission, and here in 2006 they came to Ottawa here, and you have Jim Salinger, Shiva Kumar, and we and a lot of my colleagues, we wrote a special issue. I still have quite a few copies of this, so if someone is interested, I could send on this workshop. What we talk about, I had been started talking about it quite a bit before in 2010, the impact of agriculture on climate change. But this workshop really helped to clarify there's a biogeochemical impact and there's a biogeophysical impact, which is albedo, roughness, hydrology. So agro-ecosystem, in fact, impact climate through greenhouse gas to sensible energy budget and all this. And Jean-Louis, you just gave me that a couple of days ago, which shows the same thing, but a bit more detail. Radiative forcing, climate change impact, metric for evaluating the two processes on the same scale, global warming potential, and equivalent CO2. When you talk about change in shortwave radiation, I'll show a few slides on that. It's equivalent CO2. It's not, but if you increase the reflexivity, it's like you're removing CO2 from the air, basically. Like as far. So this is quite. If someone wants to spend more time on it later on, we can get it. So in 2009, I had published this, the net effect, but you will see that I was wrong. I say negative, it reduce climate change. It's good. It reduce climate change. Positive, it makes climate change worse. So sometime I didn't know the effect completely, but these two here I will talk about: reduced tillage and reduced summer fallow. Cover crop, for example, is very, very good one. Leaving long stubble for trapping snow is very good because the snow is highly reflective. So there are many biochar is good. It could store carbon in the soil, but it could be that make the soil less reflective. So what is the impact of a change in albedo? Currently, the sensitivity, I said that before, sensitivity of the global climate system has 3.7 watt per meter square for doubling the concentration of atmosphere. So you can calculate knowing the radiative forcing impact of a management practice on albedo, the carbon equivalent impact can be calculated. And this is what I will show, the carbon equivalent impact. And that's when you decide. And the carbon equivalent impact is like, I talked a bit about before, like if you change the net radiation, for example, we had changed radiation, deciduous forest by 3 watt per meter square, by coniferous forest by 14 watt per meter square. So you see, to compensate by carbon sequestration, if you plant a tree, and if it doesn't sequester, if you plant a deciduous tree, for example, and if it sequesters, let's say 8 kilograms of CO2 per carbon per meter square, it's quite beneficial, even though it's causing a bit of warming due to net radiation. It's still beneficial, but this is quite a lot of things to consider there. So Jean-Louis and I wrote two papers recently, influence of two management practice in the Canadian prairie on radiative forcing. And he looks at the average annual CO2 drawdown between 1981 to 2016, change in two things, reduce tillage and reduce fallow. And remember, I had put, and carbon equivalent reduced fallow is considerably more than the CO2 equivalent than the biogeochemical factor. So at the time when I wrote my paper in 2009, I thought that they were this one was less, so this one is more, and this one reduced tillage even more than, and this one eventually disappeared after it's probably started to decrease quite a bit. It doesn't. This one will go on forever. But not this one. We can talk about that. Here's an example: cumulative CO2 equivalent since 1990 for. Here I show the conventional tillage due to geophysical, reduce tillage, reduce summer fallow, and even some crops, choice of crop, canola, for example, is more reflective than wheat. So it's as if you were sequestering carbon, to this is by year. So, okay. So carbon self-sufficient, we've talked about that for a long, long time, and different practices, but it's starting to decay. When farmers started to realize, we started to convince farmers should reduce tillage, for example, reduce summer fallow. Now in Canada, we used to have 13 million hectares in summer fallow every year out of the 40 million hectares. Now we have 1 million hectares in fallow. It was a way of conserving moisture, but now the timing, they do things much more efficiently, so we don't have summer fallow. And it's a good thing because now you're sequestering more carbon, but eventually this will go back to, after 30 years, it goes back to that benefit that we're gaining. We'll go back to that again. We can talk a lot about it. Natural climate solution. I mentioned already, like colleagues, AFC scientists have teamed up with Nature United, proposed 11 natural climate solutions to agriculture that could result in a reduction of 76 million tons of CO2 per year by 2030. This was published. They look at different practices like biochar, avoid conversion, keep shelter belt, don't destroy it. Manure management is the one that I will see, the one that Devin Ward and I proposed. Cover crop is very good. But all these things cost money. And we need a carbon tax for the farmers, to encourage farmers to do this. And so here we put the cost per ton. If we have $100 per ton, we could do more, like cover crop, we could do more. Yeah, because if you put cover crop, sometimes it costs money to do all these things. So biochar, for example, is quite costly because you have to make the biochar, and so it's only at $100 a ton that you get some benefit. Yeah? And you get about 6 million tons of CO2 equivalent per year of biochar. You would get that, but no, it's not being done right now because it costs too much money to do the biochar. Nutrient management, planting trees in this is not too costly to do, $10 a ton. So the one that I picked was manure management. There's a bit happening, but most of it will need money. Farmers will need money, and the idea is that it's to come and put acid in the manure tank. When the manure tank is empty in the spring, and for 4 months there won't be any methane emission. And this has been demonstrated by colleagues where they clean the tank well, but it's not. You cannot expect farmers to clean the tank well, but they clean the tank well and they have no methane emission for 4 months.